If the shaft has a diameter of 14 millimeters and a modulus of rigidity of 80 gigapascals, what is the angle of twist at A? Okay, so as we look at this, this is the same as any of the other things that we're doing. We're going to go, okay, well, my angle of twist is the sum of all the TL over JGs. So we need a new equation every time the torque changes, the modulus of rigidity changes, or the polar moment of inertia changes. So we have a uniform shaft, uniform material. We have a uniform cross-section, so that means J and G are not going to change, just the torques. So if I sit here and look at it, where are the torques going to change? The torques are going to change every time an external load is applied. So as I look from, so B is just a bearing that has no effect or no bearing on anything going on. E is where it is grounded into the wall. So if I do a quick free body diagram of my entire shaft, let me put the color back into something a little more pleasant. So if I do a free body diagram of that, what do I have? I have 150 newton meters going this way. I have 280 newton meters going this way. I have 40 newton meters going this way. And so I'm going to be left with a torque here at E that balances everything out. So we're going to be looking at a reaction torque. And so I can sum all of the torques, taking counterclockwise being positive. That has to be equal to 0. And I'm pretty sure the external torque is going to come out that way. So we'll call that the torque at E. And so what we have is we have the torque at E plus 150 newton meters minus 280 newton meters minus 40 newton meters. And so if I go and I rearrange that equation, unfortunately I can't just grab and move my inked stuff up. What we should end up with is torque of E. Let's see, 280, move that to the other side. Move that to the other side, 320, 170 newton meters. And it'll be positive, which means that I pick the right direction. So up here, 170 newton meters. So now what we have to do is that we need the internal torques, and how do we do that? Well, we're going to break it up, and we're going to look at the internals every single time an external load is plotted. So I'll be looking there, there, and there, because I'll have 3 separate internal forces. So if I just quickly look at here, if I've got 150 newtons going that way, well, that means internally at this point, I have to have 150 newton meters going along that direction. So T from A to C is 150 newton meters. Okay, everybody with me there? Now that is in the clockwise direction. And since we said that we're going along the lines that counterclockwise is positive, we're going to call that negative 150. This is important because we could have a shift twisting one way and then twisting the other and twisting back. So the important thing is just keep in mind which direction's which. And I'm using counterclockwise as positive because at the end it's not really going to matter. It's really going to come down to, okay, what happens when things are going on? Okay, so let's do the second one. So I've got 150 going this way. I got 280 going that way. That's going to leave me 130 newton meters. Now, if I do the thing, I've got 280 going this way, I've got 150 going that way, which means that I'm going to need 130 going this way to balance everything out. That's going to be in the positive direction. So TCD is going to be 130 newton meters. So we're rolling in the opposite direction. Okay, so as I get here and do a free body diagram about this cut here, got 150 going this way, I got 280 going that way, I got 40 going that way, and the only way that that is going to balance everything out is I've got to have this force here of 170 Newton meters. That's going in the negative direction, so TDE is equal to negative 170 Newton meters. Would have gotten the exact same thing if I would have started going the other way, because if I started working from this end and I made my cut here, 170 Newton meters in the positive direction, well, it's going to have to be opposed by 170 Newton meters in the negative direction, and all the way down the line. Okay, so now we have our torques. Let's move on to the next part of the problem. So what we want to find, we want the angle of twist at the end. So angle of twist is equal to the sum TL over JGs. And I can pull out the JGs on this one because solid material, same material all the way through, also the same diameter all the way through. And then I'll just do the sum of the torques times the lengths. So those internal torques times the length over which they're acting. Okay, so let's start with this stuff. So I've got J. What is polar moment of inertia? Well, it's going to be pi over 2 times the radius squared, radius to the fourth. And since I'm 14 millimeters, that's 0.007 meters. So I'm going to raise that to the fourth. And then I am going to multiply that by the modulus of rigidity, which is 80 times 10 to the 9th Newton meters squared. And so it's 1 over that. And then now I'm going to multiply it by everything else. I'm going to move that to the next line to give myself a little more room. So I have negative 150 Newton meters. How far over what length does that act? Well, A to C is 0.4 meters. And then I'm going to add to that, I have my next one, which is 130 Newton meters, because that's the internal torque anywhere between C and D. And then I will multiply that by 0.3 meters of my length from C to D. And then lastly, I'm left with minus 170 Newton meters, and that acts over a half a meter in distance. I just want to look at things really quickly here. And so I want to make sure that my units are all going to work out. So I'm going to have newtons times meters squared here. And down here, well, actually, let's write it all out and figure out to get the units at the end, because it'll be a little bit easier when we write some numbers out. So as I bash all of these together, I'll get 0, 2, 1, 2, 1. Actually, I'll get a positive 2, 1, 2, 1. So let's look at units now. So up here, these are all adding and subtracting, so I'm going to end up with newtons times meters squared. So I have newtons, meters to the fourth, meters squared down here. Well, that's going to cancel out and leave me, I'll have newtons meters squared on the top, newton meters squared on the bottom. Those all cancel out. And if you think about it, it's angle of twist. It should be in radians, so we should be fine. Whoa. Sorry about that. We should be expecting to get radians. So the angle of twist is going to be 0.2121 radians. Now that is positive. So a positive angle of twist for us is the counterclockwise direction. So what if I had went and said, okay, well, clockwise is positive? What would have happened? Well, everything would have been the same. Our directions of our torques would have flipped, and we would have just said, oh, it's 0.2121 in the clockwise direction. As I finished this video, I took a look at things and I checked my notes, and I made a small sign error in the beginning. And that was because I was being a little bit quick about sketching out the Freebody diagram and didn't do it fully, which just goes to show you it's kind of a bad idea to sometimes take shortcuts. And we have the wrong, the final answer is right. We have the wrong direction for this guy. So this guy needs to be going into the positive direction. So that would change that to a positive. And as we come down here, this should be positive 720 and not negative. So I had the signs messed up. But you're still going to end up with a 0.2121 radian angle of twist. And if you're working along this problem and wondering, it's that right there. It's my mistake because I accidentally flipped this. Okay, but that is how we would go about doing one of these. You can see there's a lot going on. It can get a little complex, so you have to be very careful with your signs as you're going through.